Hello everyone, welcome to lecture 43. So we were looking at dissipative properties and today we will continue to do that. Actually we were looking at dissipation and today we will bring in the property aspect of it. So we said dissipation is some sort of an entropy generation, right. So these are one and the same. Dissipation of energy is nothing but Ts dot. So it means that a system is out of equilibrium and it has to get back to equilibrium, and the way it does get back to equilibrium is by generating entropy, right. So we did some sort of a simple, I mean not very simple, but yeah, at least so you have to follow all the steps carefully. There is no rocket science there, it is not, it's a simple differential equation, following the differential equations from thermodynamics. So we did that to show what Ts dot is, right. So that is the power dissipated, and Ts dot actually is nothing but Vi in the electrical domain. It is sigma epsilon dot, or stress times strain rate in the mechanical domain, and so on and so forth, right. So all these are if a forcing term times a flux, right. So that gives me the energy that is dissipated, right. So in any form of energy, electrical energy that is dissipated as heat will be Vi, right. So or E times dP by dt, right. So in some sense, okay. So so a force times flux gives me an entropy change, and a generation of entropy. And so if there is a force and there is a flux, right, we said those two contribute to power that is dissipated, which is Ts dot, and this is this is dissipation. Okay. Now in general, right, so if I have an electric field, or if I have an electric field, I should generate flux of carriers, flux of electrons, let us say, right. If I have but if I actually multiply those two, I get the dissipation, right. So in general, if I have a force and a corresponding flux, right, so ideally we can so a force can be looked at as a cause and ensuing flux as the effect, right. If force is the cause and flux is the effect, there is a property that relates the cause and effect, right, and this is the dissipative property. So something that relates force times property, or so for now let us just write it as multiplication. We will see later, so times property is flux, right. Okay. So this property is a dissipative property. In some sense, so if I have Vi, I am also going to write it as half V equal to I R. So I square R or V square by R, right. So so the magnitude of resistance tells me how much dissipation I am going to have, right. So smaller the resistance, more is going to be the dissipation. Larger the resistance, or in other words, if I am going to write it as sigma of conductance, right, so it is G V square, right. So if I am just assuming that these R's and G's are some form of scalar quantities or in isotropic materials, right. So I do not worry about them being tensors, then the magnitude of G being the conductance, tells me the magnitude of dissipation. Okay. Now this is very simple, right. So if I have V equal to I R, right, so or in other words, if I have sigma E is equal to J, right. So these are some forms of Ohm's law, right. So I have, there are certain laws that connect the forces and fluxes, and these laws we know them from these are certain standard laws. I have force, I have flux, right, and what is that connects the force and flux, right. So what is the property? Okay. So so we did Ohm's law, for example. So, if I look in the domain of heat, right, I have the flux is jq, the force we said is 1 by T gradient of T, this is what we did earlier, right. So, the thermal force is just gradient of T by T, or log of gradient of log T, right. So, that is what we did in the earlier class. So, that is the thermal force. I have a flux. Now, what is the property that relates this? Jq is equal to minus k, something like gradient of T, right. So, in some sense I can say Kt is the property, Kt, this is the flux, this is the property, this is the flux, this is the force, this is the flux, and K is the thermal conductivity. And this what I have here is Fourier's first law of heat conduction. Okay. So, that introduces to us the thermal conductivity. Then if I have mass transport, I have some atoms that are moving around, right. So, some mass that is moving around, and they are moving around because of a gradient in what is called chemical potential, or gradient in concentration, that is Ci, right. And what relates these two, so very, from a Fourier point of view, I am just going to say there is a minus delta T gradient of temperature in this case there is a gradient of concentration, and what relates these two is minus di delta C, or gradient of Ci, right. So, so this is what is called Fick's first law of diffusion. And the property that comes out is the diffusivity. Okay. Now, it turns out that diffusivity and mobility are related. So, actually the dissipative property here is not really diffusivity, but mobility, right. So, mobility times the concentration will be diffusivity, right. So, that is what will come out. So, it is going to be the mobility, not really the diffusivity. That is more fundamental, let us put it that way. Okay. So, then I have a third property, again I am going to write force, flux and property. So, I did heat transport, I did mass transport, what is remaining is charge transport. I do not need such big lines because I will not do any other transport, right. Okay. So, in charge transport the force is gradient of potential, right. So, that is, or gradient of energy in some sense, right. So, that is nothing but my electric field. Flux is J of electrons, or J so a current in general. So, J of charge carriers, Jq, right, and we have our good old Ohm's law, or so I am just going to call it phi, right. So, phi as the potential. Jq is equal to minus sigma del phi, right. So, what is this? This is Ohm's law, right. So, J equal to sigma of sigma times the electric field, right. So, that is Ohm's law. Okay. Now, let us look at something else, right. So, let us put in a mechanical element to this, and let us look at dislocation transport. Now, what is dislocation transport? So, in general, so in any sort of mechanical system, if I stretch, I told you that if I plot stress versus strain, right. So, in a tensile testing experiment. So, first I have a linear regime. So, this will just expand, right. So, I am just straining the material. So, this will expand, but this is very linear. So, this is called elastic region, where so this is equivalent to stretching a spring, and all the energy is actually stored, all the mechanical energy is stored in the stretched bonds of this material, right. If I release it, it will come back, right. So, it follows the exact same trajectory, and if I release it, it will come back, right. So, there is no loss of energy. But after a while, after what is called the yield point, the upper yield point, the plastic deformation starts, which means the material will flow with application of material will flow means the strain keeps increasing, right. So, even at very small change in stress, right. So, stress is not increasing as much, right. So, okay, so let us give it some slope, right. So, there is not much increase in stress, the increase in stress is just this much, this is delta x, but I am getting already huge strain, delta small x is very large, right. So, that is called flow, the material is flowing, right. So, with very small stress the material is flowing, right. Or I can apply constant stress and get the material to flow. So, there is going to be, so that is a different experiment, right. So, this is what is called creep, right. So, there is going to be some strain rate for the material, that is the material is flowing. So, there is a flux of strain. Okay. Now, in this region of plastic deformation, one can imagine in regular metals, right. So, the flow happens by defects in a material called dislocations or dislocation motion, right, dislocations and their motion. Just having dislocations is not good enough, you have to move these dislocations and their motion. Okay. Now, I am not going into details of what dislocations are, this is what you can take some mechanical metallurgy courses to understand the fundamentals of what dislocations are, but very simply put, right. So, dislocations are these line defects in materials, right. So, a very simple illustration of dislocation is I have all these planes, right. So, then I have something which is missing, okay. So, what I have here, right. So, this missing half plane is so the boundary of that, right. So, the dislocation is actually coming out of the board here, right. So, the boundary between the missing half plane and the existing plane, right, that is this plane, the boundary between this plane and this virtually missing half plane, that is what is called a dislocation in this scenario, right. So, now if I strain the material, if I stretch the material, or if I, let us say if I shear the material, right. So, eventually the material will end up as something like this, right. So, there are going to be enough number of planes here, there are going to be one so there is going to be one step motion. If I just apply some shear on this material, right. So, there is going to be one step motion, right. So, that is the upper half, this is the bottom half, right. So, it would have moved, it would have created this one step on the surface, right. So, this step here and this step here, right. So, that is, this goes from this stage to this stage by motion of this dislocation, right. So, the dislocation starts to move and so eventually the disturbance starts going to next plane, next set of planes and eventually it ends up on the surface, right. So, this motion of dislocation is nothing but I am shearing this material, right. So, I am applying some strain on this material, right. So, motion of dislocation if you see the net dimension of the material has now changed, it has increased, right. So, the net dimension increases the net dimension, right. So, this is d plus delta d. Initially I start with only something which is d, right. So, the net dimension of the material increases, right. So, motion of increases the net dimension of the material. Right. So, as a result I can assume that the strain rate is related to the strain rate that I get, right. So, how fast or slow the material is straining is related to the motion or mobility of dislocations. Okay. So, now there are other questions that will come up, but let us very simply, right. So, assume that in all these problems, right, I have so if I go back and then see my so how I wrote the conservation laws, I said that my potential, this is like the potential, right. So, in mechanics this is potential which is stress or force, the mechanical potential which is force times displacement, that is the work, mechanical work, times the strain rate, right. This is strain rate, this is mechanical work, right. So, we always assume that this term is a so I treat this as if strain this is a conservative quantity, right. So, just like internal energy is a conservative quantity, charge flow is a conservative quantity, we said strain, we are not really sure if strain is a conservative quantity, right. So, flow of strain is a conservative quantity. Now, if I start assuming that strain rate is only generated only because of dislocation motion and number of dislocations in the material are not changing, this is an assumption. With stress, right, which is nothing but I am saying conservation of number of dislocations, then I can apply the same principles, right. So, I have a gradient of strain potential which is nothing but force, right. So that is only the case when this is valid, right. So, validity. So, I need to have some strain rate created by flow of certain defects, and these defects I call dislocations, and I am saying dislocation motion or dislocations, just like charge is conserved, I am going to assume that in a condition where dislocations are conserved, I am going to say okay, so if I have some sort of a strain some sort of a mechanical potential gradient, that is nothing but force, just like electrical potential gradient is nothing but electric field, right, and then I have a strain rate, so that is J x, or in other words I am just going to call it x dot. Then I have some equation like x dot equal to minus some property which is related to the viscosity of the material, right. So, minus I will call it nu times this force that I am applying, right. So, or the stress that I am applying, right. So, this property is the viscosity, right. So, it tells me how hard it is for me to drag the dislocation through the material, right. So, if this is large, then so even with a small force, right, I can or this is inverse of viscosity actually, not really viscosity. If this is large, even with a small force I can move the dislocations, so the mobility of dislocations is quite large, I can strain the material quite large. But if this is small, if this nu is small, then I need large force, the drag is large, right. This dislocation should really struggle to move through the material, right. So you can imagine that there is a similar scenario in the mechanics, right. So, this is electrical, let me write it in another color. Sorry, this is electrical, this is mechanical, this is mass transport, right, or chemical, and this is thermal, right. So, I have solved all the 4 I have told you about all the 4 problems, everything has a similar law, right, associated with it. But only in mechanics, right, the validity, I am being very careful in defining this, because I assume that strain rate or flux of strain, which I equate it with flux of dislocations or some defect entities that are moving, is conserved. Okay. Now, okay, so is the flux of dislocations really conserved? Sorry, are the number of dislocations really conserved? The answer is no, right. So, dislocations can be created. So, when I am actually stretching the material, when I am applying some force on the material, once it goes into plastic regime, right, the number of dislocations in the elastic regime versus the number of dislocations here, I actually not just move dislocations, but I can also create dislocations, right. So, I am actually, there is a generation term for dislocation. So, the mechanics becomes a bit tougher, right. So, I cannot really solve it by assuming that what I have is a conserved flow, right. So, it is not a conserved flow in case of mechanics, but under certain assumptions, right. So, I imagine that I created some n per centimeter cube number of dislocations here, right. Sorry, n per centimeter square, dislocations is number of dislocations per centimeter square. So many dislocations I have created here, and so under certain assumptions which says that the n is small, right. So, which means that dislocations do not interact with each other. So, I have something like 10 power 7 dislocations per centimeter square, right. So, that is a small number, right, which means there are dislocations after every there is one dislocation here, there is one dislocation here, and these two are not seeing each other. There is some strain field around this dislocation, right. So, this strain field does not see strain field 2. Okay. And they are they are not very fast moving, the mobility is small. Okay. The third assumption, the third factor that should work out for my assumption to be true, A, this is B. Okay. So, this is so the explanation for B, and C is mobility of dislocations, average mobility, I will just call this as Vm, which is velocity of dislocation or mobility of dislocation, is also small. Under these conditions, I can just assume that the dislocation number is conserved, right, and whether I talk about strain rate or velocity of dislocations, it means one and the same. So, these will be related, right. So, I can just talk about flux of dislocations instead of strain rate, I can just talk about flux of dislocations. So, strain rate and flux of dislocations are similar. But only under these conditions, right, and it is not likely that you always encounter these conditions. Okay. So, in general mechanics, that is why people do have theories which I am which I am not going to discuss in this class, different from dealing with the electrical problem or the mechanical or the thermal problem or the chemical problem, to discuss the strain problem, right. So, you will always see mass diffusion, heat diffusion, charge diffusion, all these things, so they have similar sort of mathematical framework. But when it comes to the mechanical problem where I need to look at dislocation motion, then so I have to develop other theories which are which do not follow the same framework, because there is a generation term of dislocations, right. So, generation of dislocations can exist. Dislocations are like entropy, they can be generated, they can also be destroyed, right. So, entropy so is typically generated, right. So, but dislocations can be generated, they can be destroyed. Okay. So, there is always a generation term for dislocations. Okay. Okay. So, with that caveat, let us actually come down to a very generalized framework of so if I am going to include mechanics in this generalized framework, I am always going to be in this regime, right. So, in this regime where so I can assume that the number of dislocations are conserved, right. So I have, so when I use mechanics here, I always am under under the impression that the number of dislocations are conserved. Okay. So with that, so we will come to what is called Onsagers linear response theory, where to study it looks like there is some general structure to all these properties, right. So diffusivity, thermal conductivity, then what else, the electrical conductivity, the viscosity, right, for the flow of the drag forces or the viscosity for the flow of dislocations, right. So all these have some generic structure to it, that is they relate the flux to force, right. So that is essentially what linear response Onsagers theory is. I have, let us say, many forces F1, F2, F3 and so on and so forth. Okay. Then I am going to say that the flux of 1 will depend on force 1 plus linearly depend on force 1 plus L12 force 2 plus L13 force 3 plus and so on, right. It depends on all the forces essentially, right. So I was going to say something here. So the flux, so the flux will depend on all the forces, and this is so I mean the assumption is that you are in non-equilibrium, that is why you have fluxes, right. So you have flux of certain thing, and this is flux of, let us say, species 1, right. Species 1 is moving under the influence of force 1, force 2, force 3. All these forces are thermodynamic forces that we have just seen. It can be gradient of temperature, it can be gradient of concentration, it can be gradient of electric potential and so on and so forth, right. So these can be, these forces can have different natures, right. So so they can be mechanical, they can be electrical, they can be thermal, etc. Okay. So or they can be chemical, right. So but a flux, right, so is dependent on all the forces, right, and that is where you get these cross coupling terms. We will see what that is very soon. And not just that, if I say that so J1 equal to L11 F1, you may ask why not F1 square, why not F1 cube, and so on and so forth. So this is a theory that says that, okay, so I am more or less near equilibrium. So if I am actually looking at some sort of a potential, right, so some sort of a thermodynamic potential as a function of my reaction coordinate or order parameter, I am almost so I am displaced only slightly away from equilibrium. I am not displaced so much away from equilibrium that I cannot use Onsagers linear response theory, right. I am using a linear response theory, and by using a linear response theory I am saying that my F1 tells me the restoring force to come back to equilibrium, right. So not restoring force, but my F1 is a very small perturbation that takes me away from equilibrium, right. So sorry, forget the restoring force, that is in thermodynamics, right. Here F1 tells me a small perturbation, perturbative force that takes me away from equilibrium. So what is the perturbative force? Let us say in terms of temperature, right. So I said gradient of temperature by temperature, right. So that is a valid force, that is actually the thermal force or minus of that, right. Now if gradient of temperature by temperature is not very much, right. So it is about 0.0001 or 1%, right. So that is 1%. Then okay, so my F is small enough, F thermal is small enough. But if del T is almost equal to T, right, so gradient of temperature is almost the same as okay, del T by T is a large number. So essentially I am comparing with length also here, or let me just look at this. This is 1 by L del T by T. if this thing is equal to 1, so del t, which means the change in this is T2 and this is T1. So, if T2 minus T1 is almost equal to the operating temperature, it is very large, right. So, is almost equal to T1, let us say, then so all my I have to revisit the linear response theory, right. So, I have to revisit the linear response nature of the Onsagers theory. Okay. So, by linear response I mean I am just very tiny perturbation I have. So, I have a force that took me away from equilibrium, that is okay, but it is a very tiny force, right. I am hovering around equilibrium, I am not at equilibrium, but I am hovering around equilibrium. Okay. So, okay. So, with that let us just stick to linear response theory and let us try to understand this thing. Okay. So, if I have J of so Q is some sort of a charged particle. So, now I am actually going to look at the transport of charge. I have I have some sort of a wire, right. This wire is going to transport Q charged particles, I mean charged particles with charge Q, let us say particles with charge Q. It is also going to transport heat with so with the flux J capital Q, right. So, there is heat transport, there is going to be charge transport, and I will also put the strain, right. So, there is also going to be dislocation transport or strain transport, okay, or dislocation transport. So, this is mechanically also plastically deforming, there is transport of charge, there is also transport of heat, right. So, this I am just going to write it as minus LQQ, right. So, Q is some sort of a particle, it is a charged particle, and this charged particle has a chemical potential, right. So, minus del mu Q, which is the chemical potential of this charged particle, is the chemical force, right. So, I am looking at JQ as just a particle, it is a species, it is a mass transport, that is how I am looking at it. Okay. Minus I have L so I also have a thermal gradient because I have a thermal force that is being applied. So, that will be LQ capital Q, right. So, that is my heat transport, but that has another Onsagers coefficient, a linear coefficient, minus what is the next one. So, I have some mechanical force, right. So, phi S, phi stress, right, and that will be LQ again I will write it as phi x L QX, right. Okay. So, I have a thermal I have a charge transport which is coming because not only do I have a potential that is applied or gradient in chemical potential of charges, right. So, which is nothing but the electrical potential that I apply, right. So, in fact, del mu Q will be equal to Q times del phi, phi being the electrical potential. So, these will be one and the same. So, here I am looking at this as a charged particle, but as well I can look at it as just current, right, and if I am looking at it as current I will have a del phi here, that is my force or electric field times a conductance, right. So, that is my Onsagers coefficient in some sense, right. So, JQ is just transport of charge, right. So, that is directly related to the force that is applied on the charge, right. So, the chemical force that is applied on the charge or the electrical force that is applied on the charge. The thermal force that is applied on the charge, that also so I can have a gradient of temperature and I can move the charges, or I can have just a gradient of stress and I can move the charges, right. So, it does not need only to be directly coupled to del mu Q, right. So, we or so if I have to transport charges, right, it does not need to be only by applying electric field or force, right, or so that is equivalent to the chemical force on the charged particles. Okay. So, I can also transport it by applying thermal gradient. I can also transport it by applying stress. Right, X, or this one will come out to be the force, mechanical force that I am applying. Okay. Okay, so all this is possible, right. So we will continue from here in the next class, and then actually see what Onsagers theory is saying about these cross coupling coefficients and direct coefficients. Okay. So until then, goodbye, and I will again see you in the next class.